তবে সঙ্গে সঙ্গে চেষ্টা করবে যাতে এটা তোমরা করতে পারো আর কি, মানে প্রতিটা ক্লাস
হ্যাঁ
যাতে
স্যার,
করতে পারো। ঠিক আছে,
হ্যাঁ স্যার।
ওকে, আমি ক্লাসটা
আর
শুরু করি।
কনফিউশন হলে তো আপনার ওখানে তো আছেই, আর পরবর্তী ক্লাসে একবার জানি মানে
Yes,
জিজ্ঞেস করে নিলেই হলো।
you can ask me always, but if repetitively you required any queries, that maybe just you see the video, and from that video if you understand, no problem. Otherwise you can ask me when that will in the next class or maybe
ইয়েস স্যার।
anytime. Okay,
ওকে স্যার।
okay, I will share my slide. Okay, today topics is very basics, that is fundamentals of electric field. Okay, so today we'll discuss about some basic knowledge. Already all of you know this, what is electric field, what is electric potential, what is say electric flux density, like this. Okay, so first we should know what is electric charge. So always all of you know that electric charge is a basic property of a matter carried by the elementary particles. Okay. That electric charge of two types, all of you know, because all of you know the atomic structure. From that atomic structure, all of you know that electric charge are of two types, positive and negative charges. And if you consider the case of atomic structure, all of you know in atom nucleus there are two types of elements are present. One is proton and neutron, and neutron all of you know that is having no charge or neutral, and proton having positive charge. Similarly, that all of you know that atom are neutral, so number of positive charge should be equals to the number of negative charge. So proton present inside the nucleus, number of proton present inside the nucleus, which is equals to the number of electrons surrounds the nucleus. Okay. Now, this is the basic things all of you know, that electric charge is also conserved. That is, in any isolated system or any chemical or nuclear reaction, the net electric charge is constant. Means, say after some reactions, chemically, that two different atom or two different molecule chemically react and produce some one or more atom. But before reaction, that number of charge, and after reaction, the net electric charge is constant. And you can say that algebraic sum of the elementary charges remains same. In physical terms, it implies that it given amount of negative charge appears when some amount of negative charge appear in one part of the system, that equivalent positive charge also present in other part of the system. So this is basically the physical things you have to remember. Whether you will be get say some positive charge in some of the place, means if you have to remember that equivalent negative charge also present in other part of the system. Okay, say, so suppose in charge cloud, say in this portion, upper portion, that positive charge are there, and lower portion the negative charge are there. So number of positive charge is equivalent to number of negative charge. Means wherever you will be get some charge, it may be positive charge or it may be negative charge. So there will be some, there will be equal and opposite charge should be present in other portion or other part of this particular element or particular substance. Okay, these things you have to remember. Now we come to that electric field lines. What does it mean? Say, if a charge is present, just you think about that. If a charge is present, now if you bring some other charge towards this source charge or towards the another charge, then it will be experience some force. Okay. So this is basically called the field line. So suppose this is a positive charge and this is a negative charge. And the lines are basically denoted that for positive charge, that lines are outwards. And in case of negative charge, that electric field lines are inwards. So what does it mean? If a charge is present in this portion, if a charge is present, now if you bring another charge towards it, it experiences some force. So we can say that space where the other charge will experience a force, this is basically called the electric field of that charge. Am I clear at that point? What does it mean, electric field? Electric field, when a charge is present, if you bring another charge towards it, it experiences some force at certain distance. Means if you cross that distance, that charge, or if the charge cross that distance, then it experiences some force. So suppose, just a minute. So suppose if I bring another charge towards this charge, in this portion, this charge will not experience any force. Okay. When this charge comes towards in this portion, then it experiences some force. So this is basically, you can say this is the regions where the other charge will experience some force, that is basically called the electric fields. Okay. Am I clear this?
हाँ सर বোঝা গেছে
Okay. Or in other words, that effect of fast charge, which may also be called the source charge. So this is the source charge. Extend into the space around it. This is known as the electric field, which is caused by the source charge. In this case, source charge may be positive or may be negative, but surrounding this field is basically called the electric field of that particular source charge. Okay. Now, if there
স্যার
is
একটা
no,
কোশ্চেন আছে
huh?
বলছি স্যার ওই সোর্স চার্জটা কতটা ডায়ামিটার ফিল্ডটা কভার করবে ওটা ওর কতটা চার্জ আছে তার উপর ডিপেন্ড করবে তো
Obviously, that electric field or the space, that is basically depends on the magnitude of the charge. Okay, if the magnitude of the charge is more, so its surrounding field will be more. If the magnitude of the charge is less, so surrounding field will be less.
ওকে স্যার
Okay. If there is no charge in space, then there will be no electric field. If you say that magnitude of this charge is, source charge is 0, so there will be no space or no electric field surrounding this. Okay, these things you have to remember. And maybe in your mind you have a questions why the lines are say outward in case of positive charge, or in case of negative charge, why it is inwards. So suppose if you bring a test charge, generally test charge is positive, so it experiences a force, that is the repulsive force. If you bring a test charge, say positive charge, towards this source negative charge, it basically attracts this test charge. That is why that field lines are generally, this is the convention. In case of positive charge, that field lines are radially outward, that is the field lines are outward direction. In case of negative charge, these field lines are inward direction. Okay. Now you will see, already I show that field lines of positive charge and negative charge, but this is you see the test charge will move away from the positive source charge and move towards the negative source charge. This is the convention. Okay, the test charge will move away from the positive source charge due to that repulsive force and move towards the negative source charge. Accordingly, the direction of the electric field lines are such that they originate from the positive charge, means they are originated from the positive charge, and they are basically terminated in the negative charge. So if we consider that two charge, they are adjacent each other. So what is the convention? That in case of the positive charge, that field lines are originate from the positive charge in these directions, and these field lines are terminated in the negative charge. If the two charge, they are oppositely charged and they are adjacent each other, so their field lines will be oriented in that fashion. And you have to keep in mind, or you have to remember, this is the conventions we are follow in case of field lines for positive and negative charge, that electric field lines are originate from a positive charge and it terminates in the negative charge. Okay. And what is the SI unit? According to the SI unit system, 1 coulomb of source charge give rise to 1 coulomb of electric field lines. Okay. Now, I want to give you the concept of lines of force, that is equivalent to the charge and electric flux density. Lines of force can be designated as electric flux. Means you can say that number of lines which is equals to the magnitude of the number of charge, equal to the charge itself. So electric flux is basically what? Electric flux or flux lines, number of flux lines which is equals to the charge or magnitude of the charge, and its unit in coulombs. Like magnetic flux line, electric flux lines, number of electric flux lines for a particular charge, that can be denoted by num, which is equals to the magnitude of the charge. Now, like magnetic flux density, what does it means? Magnetic flux density, all of you have idea about that flux density, magnetic flux density. What is this? Magnetic flux density is basically denoted by what? All of you know. Anyone?
B समान phi by area, flux by area.
B is denoted by B is basically denotes the magnetic flux density, and magnetic flux density is basically flux per unit area. Okay, so similarly here also electric flux density is equals to electric flux per unit area, where the area is normal to the direction of the flux. So if I consider that charge is Q, so for that case, electric flux density in this point P due to the charge Q is equals to, and D is basically denotes the electric flux density, which is denoted by charge per unit area. So here we consider that spherical configuration, that is why that charge per unit area is Q by 4 pi r square, and UR is basically denotes that unit vector. And mind that this electric flux density also a vector quantity. Okay. So UR is the unit vector in the direction of R at P, and you have to remember, because frequently we have to require that unit of electric flux and unit of electric flux density. Unit of electric flux, which is nothing but a charge. So electric flux is denoted by unit is Coulomb, and in case of electric flux density, that is basically equals to Coulomb per meter square, because Q is represented in Coulomb and area is basically in meter square. So electric flux density is equals to Coulomb per meter square. Okay. Now we come to the very well-known law. All of you know that Coulomb's law. All of you, I think all of you have idea about that Coulomb's law. If the two charges separated by some distance, it experience some force. That force may be repulsive or attractive, depends on the magnitude of the, depends on the polarity of the charge. I think all of you know this Coulomb's law. From 10th onwards, in 10th standard, all of you studied this Coulomb's law. Okay, so here the same thing, but you have to remember that magnitude of the electrostatic force of interaction between two point charges is directly proportional to the scalar multiplication of the magnitude of the point charges and inversely proportional to the square of the separation distance between the point charges. And the electrostatic force of attraction acts along the straight line joining the two point charges. If two point charges are of same polarity, the electrostatic force between them is repulsive. If they are opposite polarity, the force between them is attractive. Okay, I think all of you have idea about this Coulomb's law. Any doubt that if the two charge separated by some distance, then it experiences some force. That type of force, repulsive or attractive, that will be decided by whether the charge is two charges are same or like charge or opposite charge. And that force, if you want to measure the force is directly proportional to the product of these two charges and inversely proportional to the square of the distance. Any doubt up to this discussion?
No, sir.
Now you see, we can represent that. Any question? Any queries? Any doubt?
Sir,
হ্যাঁ, কি বলছো বলো, বুঝতে পারছি না। বোঝা যাচ্ছে না, শোনা যাচ্ছে না?
হ্যাঁ স্যার, শোনা যাচ্ছে। মানে বলছি এই পেজটা যেটা এখন আমরা দেখছি, এই পেজ কোন বলবো
কথা শোনাই যাচ্ছে না, কথা একদম কেটে কেটে যাচ্ছে।
দরকার হলে কেউ কোশ্চেন থাকলে পরে আমাকে জিজ্ঞেস করো, ক্লাসটা Continue করুন।
ঠিক আছে স্যার, কন্টিনিউ করুন স্যার, কন্টিনিউ করুন স্যার।
Two conditions are fulfilled by just you see here the two charge, positive charge, and if I consider negative charge, now force, if force of attraction between these two charge, force of attraction, that is F12, or if I consider that Q2 is more than Q1, then force of attraction also represented by this, because these two charges are opposite in nature, so their force between them is attractive. Either you can measure the force in terms of F12. F12 is basically denoted by the formula Q1 plus minus Q2 by 4 pi epsilon 0 R12 square. R12 square is basically denotes that difference between the distance between the two charges, and similarly you can represent that also as a F21. So for that case, that will be represented in there. Always we consider that charge is Q1, either this will be minus Q2 or plus Q2. If that second charge is minus, then the force between these two is attractive. If this second charge is positive, so for that case force between these two is repulsive, and their representation in that form, either you can represent that force means from 1 to 2 means in that directions also F12, or you can represent F21. So in both the cases they are more or less similar, only your notation is different, and the orientation of the unit vector UR21 is this and UR12 this, so you have to represent in that form. Okay, and that constant of proportionality K, which is appears in this case, that is 1 by 4 pi epsilon 0, that constant of proportionality is basically 1 by 4 pi epsilon 0. And all of you know what is the formula of epsilon 0? Sorry, what is the value of epsilon 0? Frequently you have to remember this value. What is the value of epsilon 0?
4 pi into 10 to the minus
854.
No, 4 pi into 10 to the power
No,
minus
sir,
7.
8.85
Oh, 8.854.
Sir, 8.854 into 10 to the power minus
into
12.
10 to the power minus 12.
12 farad per meter. Epsilon 0 value is 8.854 into 10 to the power minus 12 farad per meter. And one of you says that value of 4 pi into 10 to the power minus 7. This is also a well-known constant that is basically called what? Mu0, permeability of the free space. Okay. Now frequently you have to remember that constant either in that form 1 by 4 pi epsilon 0. If you replace that epsilon 0 by 8.854 into 10 to the power minus 12, in your calculator you will be get that value. So approximately we remember that value as a 9 into 10 to the power 9 Newton meter square by Coulomb square. Okay, because force is Newton, so from that you can replacing that force by Newton, charge by Coulomb, and area by meter square. So ultimately you will be get that constant unit is Newton meter square by Coulomb square. Now you see in case of Coulomb's law, force is proportional to the product of two charge, and force is inversely proportional to the what? Square of the distance. Now all of you know similar type of law that is for applicable for some other system. What is the law?
So gravitational.
Yes, true. This is the gravitational law. Now what is the gravitational law? What is the force? Gravitational force, that is again this is the product of what?
মাস Product of mass.
Mass and inversely
Mass.
proportional to the distance. Okay. Now, just you from your basic knowledge, just you try to give me answer. What is the difference between these two? Means from which point of view we can find out the difference between these two laws, Coulomb's law and say gravitational force, or you can say Coulomb's law means what? Electrostatic force and gravitational force. What is the difference? Just for up to these discussions, if you think about that, more or less these two forces are proportional to their charges and proportional to their mass and inversely proportional to the square of the distance, but there is something difference between these two forces. Just you think for a while and try to give me the answer. It is very simple. Electrostatic force, what is the nature of electrostatic force? Nature means it may be attractive or repulsive. Okay. But gravitational force?
Only attractive.
Only attractive. Very good. So this is the difference between gravitational law, gravitational force and electrostatic force. Okay. And another thing is, if you compare magnitude wise electrostatic force and gravitational force, electrostatic force is much higher than the gravitational force. But electrostatic force, if the two charges separated by a long distance, more or less this charge or this force is what? Zero. If the distance between two charges, say very long, or you can say infinite, so for that case electrostatic force is zero. But in case of gravitational force, that is basically applicable for a long distance also. Means you'll be feel that force at very long distance also. Okay. So this is the difference between that electrostatic force and the gravitational force. Electrostatic force is more applicable for when the two charge will be closer to each other. So there will be an existence of electrostatic force will be more. Okay. Now we come to electric field intensity. Okay. Electric field intensity. What electric field intensity is basically called. So just you think about that. From that formula, you can easily see that electric field intensity is basically force per unit charge, which is the measurement of electric field intensity. Okay. But what does it mean? Say suppose a charge is present here. Okay. If you bring a charge towards it, so it feels some force. Okay. So that is basically called the electric field. From if this charge, that test charge enters into the field, it experiences some force, and that measurement of this electric field, that will be by electric field intensity of this particular point, say P, which is located at a radial distance r from the source charge Q1, and that is basically the force experienced by a unit test charge of positive polarity at that point. Mind that you have to remember that test charge is generally we consider that test charge having positive polarity. When you want to bring a unit test charge towards a source charge, here it is plus Q1. So you will be face a force, and if you measure that force at that particular point, so that force is basically denoted by in terms of electric field intensity. That is, electric field intensity is basically equals to force per unit charge. And force is basically what? Force is basically the what? Force when we bring a unit test charge. Unit test charge means what? Magnitude of the test charge is 1. Okay. So according to the formula of Coulombs, F is equals to what? Q1
Q1 into Q2 by R square.
Q2. Here Q2 is equals to, say, if you consider Q2, so Q1 Q2 by 4 pi epsilon 0 epsilon R square. Okay. Now this force is divided by Q2. So ultimately you will be get that electric field intensity formula is Q1 by 4 pi epsilon 0 epsilon R square. And what is the unit of electric field intensity? Unit of electric field intensity is generally represented as volt per meter. Now this is your task. How will we get that electric field intensity is volt per meter? From that definitions, will we get that electric field intensity is basically what? Electric field intensity is basically, here you see, it is basically denoted as force. Force is Newton divided by Coulomb, Newton per Coulomb, and generally all of you know that electric field intensity unit is volt per meter. Okay. Now, if you know the electric field intensity epsilon, electric field intensity E, so you can easily represent it that electric flux density in terms of electric field intensity. What is the formula of electric flux density? Electric flux density is charge per unit area. Okay. So here you see charge per unit area. Previously we denoted as that charge per unit area is equals to this Q by 4 pi epsilon R. Okay. If you multiply this, means if I want to find out in terms of electric field intensity, so D is basically equals to epsilon. If you multiply this by epsilon, so that is basically the representation of D, because epsilon cancel out, because epsilon is the product of epsilon 0 into epsilon R. So epsilon 0 epsilon R cancel out. So ultimately you will be get that Q by 4 pi R square. So this is basically the expression of electric flux density in free space. Free space epsilon R value is 1. So that is why it is multiplied by epsilon 0 into ER. And in case of any particular medium except free space, so that will be denoted by epsilon 0 epsilon R into ER. Okay. বোঝা গেল কিনা বলো? ঘুমিয়ে বললে হবে না?
না না স্যার
স্যার Q2 টা স্যার কোথায় কোথায় গেল স্যার? যেহেতু আমি Q1 পজিটিভ চার্জ আর এখন সেট ডিসগল যেটা দিচ্ছি ওটা Q2 টা স্যার কি হবে গেল স্যার?
যে অ্যাজিভ যেন টেস্ট চার্জটাকে আমরা বলছি Q2।
আচ্ছা
এখানে
ওকে স্যার ওকে স্যার
Q1 Q2 বাই 4 পাই এপসিলন 0 এপসিলন r স্কয়ার। ঠিক আছে?
হ্যাঁ স্যার ঠিক আছে।
এবার just you if you have your notepad with you, so if you write simultaneously side by side, D is equals to Q by 4 pi r square and E is equals to Q by 4 pi epsilon 0 epsilon r square. So from that, if you replace Q by 4 pi r square by D, so you can able to write dr is equals to epsilon 0 epsilon r er, or dr is equals to epsilon 0 epsilon r er. Here why I written er, because electric field intensity at that point P, which is
Distance of r.
distance r. That is why within bracket we are writing r. Okay. Generally, we have to remember that formula. D is related with electric field intensity in terms of epsilon. In general formula, D is equals to epsilon E. In general formula, D is equals to epsilon E. In case of free space, sorry, that pointer is not controlled. So D is, you have to remember this equation, D is equals to epsilon E. So here, in case of free space, epsilon is equals to epsilon 0. And in case of any other medium, epsilon is represented by epsilon 0 into epsilon r. Okay. Now we come to a well-known thing, all of you know, that is the electric potential. Okay. Now, what does it mean? What is the actual significance of electric potential? Now, all of you know from that your basic definitions, already all of you had studied these things in your 10th level, that work done in a moving a unit positive charge from one point to another within an electric field, or to bring a positive charge from infinite to a particular point, that work done is basically called the electric potential. Okay. When you are bringing a test charge from infinite to that particular point, it experiences some force. Okay. So electric field intensity at any point within an electric field is defined as potential energy per unit charge at that point. And electric field intensity is a vector quantity, but electric potential is a scalar quantity. And why the electric potential is scalar quantity, we'll discuss these things in next slide. And unit of electric potential is volt, all of you know, which is equivalent to joules per coulomb. Why joules per coulomb? Because we define that electric potential is defined as potential energy per unit charge. So what is the unit of potential energy? Unit of potential energy is joule. Per unit charge, that is unit of charge, is coulomb. So you can easily remember the definition of electric potential and electric field. Electric field is basically what? Electric field is force per unit charge, and electric potential more or less similar, but instead of force, this is potential energy per unit charge. And sometimes we are basically interesting to find out the potential difference between the 2 points. So that definition is like that. Potential difference is work done in moving a unit positive charge from one point to another within an electric field, that is equals to the difference in potential energy, and hence the difference in electric potential. Okay. Now, in your mind, you have to think about that why the electric potential is a scalar quantity. Electric potential is a scalar quantity when you moving a charge or moving a positive charge from say 1 to 2. So for that case, it experiences some force, but each and every point that direction of the force is changes. Okay, so that does not depends on the direction. That is why it is electric potential is a scalar quantity. And how you will be measured? That force experienced by a unit positive charge at point 1 is electric field intensity. Then the potential difference between the point 2 and the starting point 1, which is given by phi 2 minus phi 1, where phi 2 is the potential of that point 2 or this point 2, and potential at the point 1 is denoted by phi 1. And we know that electric field intensity at that particular point is E, and it is basically displaced by from 1 to 2 is distance is dl. So if in this case it will be multiplied by my E into dl, that is phi 2 minus phi 1 is equals to minus E into d. When we are bringing a charge from one point to another point, so that the potential energy is basically decreases. That is why this minus. In equation, E into dl is the work done by the field force in moving a positive charge from point 1 to point 2. Okay. In this case, potential energy of the point 2 will be lower than that of the point 1. Hence, the potential difference will be negative. Here you see potential of that point is lower than the potential point 1. That is why this phi 2 minus phi 1, we incorporated these things is minus. If you represent that thing in phi 1 minus phi 2, that is the potential of point 1 minus potential of point 2. So that is you can able to represent that as a E into dl. But general convention is that when we are bringing a charge from this point to this point, it has basically lose its energy. So potential of that point is lower than the potential of the point 1. Okay. Now in this figure, if you see that positive charge moves through a certain distance here, certain distance L within an electric field from point 1 to point 2, then the magnitude as well as direction of may not same at every location along the path traversed by unit positive charge. When a unit positive charge moves from this place to this, the directions, this is the important thing you have to remember, the direction of may not be same at every location along the path. When it is moving in this directions, and if you measure that direction, if you measure in this point, so in every point the direction is not same. So in that case, potential difference between the point 2 and 1 is evaluated by integrating that right hand side of the equation. Right hand side of the equations means this side, that if I want to find out the potential difference between 1 and 2, so we have to integrate this side with the limit 1 and 2. So this is basically the equation. So suppose you want to find out the potential difference between 1 and 2, and that is they are located at L meter apart. So for that case, find out that potential difference between these two. If you know that elemental potential between point 1 and 2, that is basically E into dl. But in case of actual case, if I want to find out the potential difference between 1 and 2, they are apart from each other at L. So for that case, it is basically you have to integrate this right hand side from 1 to 2. Okay. So the point 1, now in that previous case, point 1, if you chosen that point at an infinite distance with respect to the source charges causing the electric field, then the potential energy at point 1 due to the source charges will be 0. And hence the electric potential phi1 will be 0. So then you can write that equation in that form. If you consider that point 1 at infinite distance, so for that case, that potential of that point is equals to 0. Now in previous equations, if you replace that phi1 potential is equals to 0, and your limit will be in that case from infinite to 2. So you can able to write these equations in that form, that phi2 is equals to minus infinity to EdA. So this equation shows that electric potential at a point in an electric field can be defined as that work done in moving a unit positive charge from infinite to that. This is the basic definitions, or the definitions already you studied this. So it can be defined as the work done moving a unit positive charge from infinity to that point. So work done is independent of the path traversed between the two end point. Hence the electric potential is a conservative field and is a scalar potential. Why is it so? So if you find out that either charge is traversed in this directions, or it may be traversed in this direction, or it may be traversed in this way, so that does not depends on the which path it is followed. So that is why this electric potential is a conservative field and it is a scalar quantity. Okay. Now you have to remember, or you have to know, what does it means equipotential? What is the meaning of equipotential? Any idea?
স্যার একটা এরিয়ার মধ্যে সব জায়গায় চার্জ সমান আছে।
So suppose in a particular field, if you consider some point where you'll find that potentials are same. Okay, so suppose in previous case, what we seen that work done in moving a unit positive charge infinity to a given point within an electric field, that could be same for several points within that electric field, depending upon the distribution of electric field intensity vectors within the field region. Means within the same electric field, if some point they are at same potential, then these lines are called the equipotential line. Okay, and that will be much more clear if you consider that, say suppose these lines are at the same distance from a particular charge, these points, so they are maintain that equipotential line. Similarly, here these points are also maintained at certain distance, so they are also equipotential line. Okay, so in that way, electric potential of all such points will be same. This is the primary condition for the equipotential line. We can draw a line between the points or among the points where the points maintain at same potentials, or you can join the points, those points are in same potential, then this line is called the equipotential line. All the points are called electrically equal potential. If all these points are joined together, then one may get a line or surface on which every point has the same electric potential. Okay. Now here, these things you have to frequently face, that uniform field and non-uniform field. What does it mean? Uniform field means everywhere if you measure the field, that field value is same. So this is the configurations only you will find these applications in case of parallel plate. In case of parallel plate, if you connect these two plate with some battery source, then the lines, field lines, which links the two plates, they are basically the uniform field lines. And this is two figures. This is basically shows the uniform field. This is non-uniform field. Why this is uniform field? Because in this system, figure A shows that equipotential lines and electric field lines for an electric field is constant everywhere. If you measure the electric field here, or if you measure the electric field here, everywhere you will be get that electric field is constant. But in case of figure B, this concentric circle, they are maintained at same potential. That is why this point, these lines are they call equipotential lines. But if you measure the electric field here, that electric field here, and if you measure the electric field here, so in the two cases you will find that electric field is different. Means here the electric field varies with the positions and it is not called non-uniform field. Where you'll get that electric field is uniform irrespective of the position or irrespective of the particular position. So then this field is called uniform field. And if it is varies with the positions, then this field is called non-uniform field. Okay. Now you have to remember, or you have to know what does it means electric potential gradient. Frequently we are used that electric field intensity, electric field gradient, they are synonymous, but there is a slight difference from the field theory point of view. What is the difference between electric potential gradient and electric field lines? Mind that electric field lines and electric potential gradient, they are more or less same. But what is the difference? In case of electric potential gradient, it is defined as positive rate of change of electric potential with respect to distance. Positive rate of change of electric potential. Electric field, also in previous slide we represent that electric field is the electric potential with respect to distance, but that rate of change is positive. It will be more clear if you consider this 3 point 1 to 3. Potential of this is all are equipotential lines. Okay, and the potential of the line 2 is phi. Potential of the line 1 is phi plus del phi, just slightly higher, and potential of the line 3 is phi minus phi. Now, if anyone travels from 2 to 1, means it will be transferred from lower potential to higher potential. That point P on the equipotential 2 having an electric potential P. Now, if one moves to any point on the equipotential having an electric potential phi plus del phi, so what is the potential difference? Potential difference between these two is phi plus del phi. But the minimum distance between this equipotential 1 and 2, that will be denoted by del n. Okay, this is the del n. Hence, the greatest rate of change will be along the normal to the equipotential. So always, this is the normal to the equipotential. And similarly, that potential gradient is basically denoted as change of potential, that is potential difference plus del phi divided by change of distance, that is del n. Okay, but if you want to define that electric field intensity, instead of moving towards the positive directions, if it's towards the negative direction means change in, instead of positive rate of change, it will be changed to negative rate of change like this. So when one moves from equipotential 1 to equipotential 2, So equipotential 1 to equipotential 2 along the normal distance del n, then the potential drop is phi and the work done by the field forces is given by del phi is equals to E into del n. So that is E, that is the magnitude wise, E is del phi by del n. Here you see, if you move instead of 2 to 1, if you move from 1 to 2, so there is a potential drop, and that potential drop is basically del phi. And what is the distance between these two potential points? That normal distance is del n. So electric field intensity can be denoted as del phi by del n, but instead of increasing the potential, that is the decreasing potential. That is why we can represent that grad electric potential gradient or grad phi or electric field intensity, they are more or less magnitude wise, or they are magnitude wise same, only that difference is in sign. Why? Because grad phi acts along the directions of increasing potential. That will be clear. Grad phi is basically direction from positive directions, and electric field intensity directions from negative directions, where the potential drop from phi to phi minus phi. But in case of gradient, potential gradient, it is that gaining the potential from phi to plus phi. So this is the only minor difference. Potential gradient with respect to positive rate of change of electric potential. Electric field intensity is basically the negative rate of change of electric potential. So you have to remember these things. This will be required frequently. E is equals to minus grad phi, or electric potential gradient and electric field intensity magnitude wise they are similar, but if you consider that sign is different, they are acting in opposite directions. Okay. Now we want to find out, because these things will be required, that electric field intensity in a particular direction. Now in the figure, if you consider that potential difference phi 1 minus phi 2 between 2 points, it will be denoted by phi, and it is denoted as minus E into del L. So this is the convention for minus. Why we consider that? Because we are losing that potential from 2 to 1. So phi is equals to minus E del L, where del L can be represented by, normally it is, you can see that E is having a angle here with del L is theta. So that directions is basically that del L cos theta. So del lie along the directions, if del L lie along the directions of the x-axis, so that can be termed as a del x. So equation can be rewritten in terms of x. So Ex is equals to minus phi by del x. Just instead of del L, if I consider that as a direction of x-axis, because here always you have to consider the 3D, 3-dimensional. So for that case, every directions you have to consider what is the value of electric field intensity. Now similar things, E is equals to minus of del phi, that is potential, by del L. Now x directions, if I denoted by that is del x, so that will be related as minus del phi by del x. But in case of instead of discrete variations, if you represent in continuous variation in electric potential, that can be represented by electric field intensity. This similar thing, instead of discrete variations, you can represent it by del phi. Instead of del x, you can represent, this is representation for the continuous variations of the electric potential, and this is the representation in discrete variations. Okay. Now similarly, if it is a 3D system, 3-dimensional system, so In Y and Z directions, it's also having components, then that can be similarly represented by electric field intensity in Y directions and electric field intensity Z direction is this, or we can represent total electric field intensity vector in terms of the three components in three directions, that can be represented by Ex into Y, where I is the unit vector, Ey into J, J is the unit vector in the Y direction, K is the unit vector in the Z direction. So that can be represented by total electric field intensity is summation of the electric field intensity in X direction, summation of the electric field intensity in Z direction, and summation of electric field intensity in K directions, or you can say Z direction, sorry. So if you replace Ex, Ey, Ez by del phi by del X, del phi by del Y, del phi by Z, so this will be looks like this if you take phi common. So this portion is basically represented as a del operator. Del operator means this is del of del Xi, del of del Y, J, del of del Zk. And frequently these things will be used in the next few lecture class, that is basically denoted as del operator, and which is an interesting operator. Why it is interesting? Because all of you know, after the study of electric field and electric potential, electric field is a vector quantity, but electric potential is a scalar quantity. If del operator multiplied with scalar quantity, then the scalar quantity is transferred to the vector quantity. When it acts on a scalar quantity, means electric potential, acts means when it is multiplied by this scalar quantity, that result is a vector quantity. And physically, this results into the special derivative of the scalar quantity, that is the gradient of the scalar quantity. So in this case, del acts on the scalar electric potential, it results into the vector quantity electric potential gradient. Okay. Up to these discussions today, I will stop here. If you have any questions up to this discussion.